Hi! It is time to run our logistic regression model. You may remember from the PD model that the logistic regression class in sklearn wasn't able to give us p-values for the estimated regression coefficients, so we had to alter it a bit. When estimating the LGD, we are facing the same issue, so let's copy the code we wrote and use the same class here. Alright. Now we can run the model to estimate if the recovery rate is equal to 0 or is bigger than 0. Let's set regression LGD stage 1 as an instance of the logistic regression with p-values. Then we fit regression LGD stage 1 with LGD input stage 1 train as input variables and LGD target stage 1 train as targets. So far so good. We have successfully created the model. But what does it tell us? Well, we can copy the code we use for the PD model to display a summary table with the regression coefficients and their p-values. We will store the names of the independent variables in the features name list. Of course, we need to change the name of the logistic regression instance here, where we take the coefficients, here, where we take the intercept, and here, where we take the p-values. Now, let's run it. Amazing! We estimated the first stage of our LGD model. Let's explore the regression coefficients. Most of them aren't statistically significant. This means that if we throw these variables out of the model, its predictive power would remain unchanged. Or we may as well keep them. Either way, it won't make much difference with respect to how well it predicts the recovery. More often than not, we prefer to leave them out in order to simplify the model. Let's interpret a couple of coefficients as we did with the PD model. The only tiny difference here is that we have continuous variables and their coefficients don't reflect if they belong to a category of an original independent variable or not. Instead, they reflect the change in the logarithm of odds that for a unit change in the respective continuous variable. For every unit increase in funded amount, the logarithm of odds of recovery rate being greater than 0 will increase with about 0.0001. Note that the format of numbers we see here is known as E notation. When you have E minus 0.4, this implies that we should divide the number we see by 10 to the power 4. For instance, 1.078814 E minus 0.4 is equivalent to 1.0788814 divided by 10 to the power of 4. This equals 0.0001. By the way, whenever we have a plus sign, we multiply by 10. For example, 5.42 E plus 0.2 would be equivalent to 5.42 times 10 to the power of 2, or 542. Alright, let's continue with the other variables. If we take debt to income, for every unit increase in debt to income, the logarithm of odds of recovery rate being greater than 0 would decrease with about 0.0169. Okay, you can spend some time on the coefficients. However, what matters most here are our model's predictions. So let's test our model. To test the model, we use the test data. First, we must select the same features we used to train on. So let's select the relevant columns by using our Features All list. Then, we can drop the reference categories from the Features Reference Categories list. Alright. To obtain the predictions from the test data, we call the Model Predict method on our Stage 1 regression model. We can store the results in the variable yHat_test_LGD stage 1. What we get are raw predictions about the recovery rate. Although that's very useful, it would be even better to get the estimated probabilities of the recovery rate value. After all, we are practically trying to distinguish if it is going to be 0 or above 0. That's why we coded recovery rate equal to 0 to correspond to 0 in the dependent variable and recovery rate greater than 0 to correspond to 1. Once again, to find the probabilities, we apply the predict_proba method instead of the predict method. It would be sufficient to keep only the probability for recovery rate greater than 0. And here is how we get an array that contains only the probabilities for recovery rate greater than 0. Awesome! The result is a data frame which contains the probabilities related to the test inputs. To really assess the accuracy of our model, we must compare them with the actual values, or the test targets. Let's wrap up here and assess the accuracy in the next lecture. Thanks for watching.